And I'm just gonna share my screen. People who are late will just join us late, I guess, and they can catch the recording from tomorrow onwards. Where was I? I stopped at, well, in fact, before I start actually, I did share this with you. This is basically a list of formulas. So it's very important that you are able to actually go through these list of ions, be able to, as you see the name, you are able to kind of go through the formula in your head, and whatever you couldn't, you should be able to, check later on. Important to also write it on paper and not to just read it as it is. Of course, these are labeling apparatus. If you have problem with spelling, you know that you made a mistake before. You need to be very careful. And this is the 2 pages test. I purposely erased the ion here. I purposely erased the formula of the ions. So you need to know the formula of the ions if you want to know the test for it. And of course, the test and the test results are very important stuff. Looks like only 2 pages, but then everything in these 2 pages is one whole topic that we're going to review today. So where was I? The last place I stopped, we have covered all that. Electrolysis, I covered in year 10. We just did it, before the school shutdowns, and you already done the test. So I'm not going to go through that because you can review those yourself. And what else? Electrolysis, fuel cells. We just did this chemical energetics, and you will have the topical test on this whole topic next week. Bear in mind that you also have the experimental bit, which is the alternative to practical bit, and that is related to some of those questions which you had done before, like the neutralization question or some other kind of heat loss, heat absorb kind of physics experiment as well. I guess the one that I'm going to go through today will be your year 9 concept on the physical and chemical changes and describe the differences between them. There aren't many I can tell you, but what I can roughly tell you and remind yourself is physical change, meaning it's just the chemical composition does not change. So the chemical identity or the chemical composition does not change. There's the most important concept about physical change versus chemical change. So chemical identity or composition does not change. Can I just double check? Can people hear me all right? I'm afraid I've just muted myself. Can people hear me all right?
Yes.
Yes.
Okay.
Yes.
All right. Okay, that's all right there. Okay. So in terms of chemical changes, we talk about chemical identity has changed. So that's the first thing you have to think about on the surface. But then you also have what happens at the particle level. This is now at the particular level, things which you cannot see with your eye. You know about kinetic particle theory, what happened to the particles, things you cannot see with your eye, and therefore you have to try and think about what happened on the surface and what happened at the particular level, where you can represent the, with small spheres. Of course, the particles could be ions, could be electrons, etc., depending on structure and bonding. There is a precedence to everything, something before something. So you need to try and consider why the topics were lined up in such a way, leading up to this idea of chemical reactions, chemical changes, and physical changes. A lot of chemistry come down to chemical change. Not a lot of chemistry come down to physical change, but we know about physical properties. Physical properties are like melting point and boiling point. Physical properties are like density. Physical property are like appearance. But what appears on the surface doesn't actually tell you much about what happened at a particular level. Density of solid is usually higher than liquid, higher than gas, because when you go from solid to liquid to gas, if you have 1 gram of ice, when that 1 gram of ice melts, you're going to get 1 gram of water, and you're going to get 1 gram of steam. Going from here, the liquid to the gas, so you have increase in your volume, but the mass is still remaining the same. Therefore, your volume increases, your mass is the same, your density of the steam will be much lesser than the density of liquid. I shouldn't have chosen this example because this is a very special example because of here. You know that ice floats on water. This is only very specific to water alone. So we know that iceberg, when you go to the North Pole and South Pole, the ice floats on water. So what does that tell you about the density of ice and the density of water? Can anyone tell me? Let's ask, I don't know, Lukman, are you there? Hello, hello. Are you there, Lukman?
Yes.
Okay, so ice floats on water. Which one is denser? Is it ice or is it water?
It's the same because it only changes the physical properties.
But if something floats on something, you know about, you love ice drink, right? Ice coffee, ice Milo, or whatever. So if ice floats on water, which one? They must have different density, because if they have the same density, one would not float in the other. Do you know the concept of floating?
Yes.
So it's about density. So the mass is the same, but density is not mass, as you know from physics. Density is not mass. What is density equal to?
Density is volume over mass.
Nope. Density is mass over volume.
Kebalik.
Density is mass over volume. Okay, doesn't matter when you get it the other way around. If you get it the other way around, it's wrong. It's wrong because you know this is some basic science here. Density is mass over volume. The density of water. So water is something that you would have come across in physics. Is 1 gram per cm cube. So that means when you have 1 gram of water, is 1 cm cube. When you have 1 cm cube of water, is 1 gram. But then in ice floats on water. Ice is less dense than water. Ice has lower density than water for the same mass of H2O. So the volume of water must be smaller than the volume of ice. This is very special. This is unique. This is very unique to just H2O alone. It's got something to do with the structure, which you don't really learn in O level. But I just want to remind you that this is something from your physics. These are physical properties. We talk about changes of state or mixing. When you mix something together, you have a mixture that is physical change. But when you undergo a chemical reaction, then your atoms, your molecules can break covalent bonds, and then they will undergo a chemical bonding where they form bonds. Could be ionic, covalent, metallic. Well, actually metallic is element, but could be ionic or covalent bond as a result of a chemical change, as a result of chemical reactions. That is when you know you have chemical changes. So be very careful there. Now that's it really. We move on to redox. So redox is quite a big topic on its own. I know for a fact that a couple of people skipped the whole topic last year, and that is probably why they did not understand anything electrolysis at all. It was a whole topic last year, it was for a couple of weeks, and there is nothing that can be done to turn back time because time does not go back. Okay, use a Roman numeral. So we use a Roman numeral like 1, 2, 3, etc., up to 7, 8, blah, 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 to indicate the oxidation number of an element. So for example, you have come across this name. It's called potassium manganate, MANGANATE, bracket VII. So that means that is oxidation number of 7. So VII that stands for oxidation number of 7. This is your purple colored solution as you have used it for your titration experiment KMNO form. The overall compound has no charge, so it's 0. Potassium is a group 1 metal. A group 1 metal, when they form compound, will have a +1 oxidation number. Manganese there, and then you have 4 of the oxygen, each of which is -2. And then we know oxidation number must have sign as well as value. It's very important to have the sign as well as the value, because without the sign, oxidation number has no meaning whatsoever unless it's 0. It could have plus, it could have minus, unless it's 0. So now there are a couple of formulas that you really need to know the names of, and it goes back to this table. Of course, this table was taught to you in year 9, under chemical formula before redox. So all of those things there. So dichromate, di means 2. The ATE means is combined with oxygen. The 6 there refer to the chromium +6. It's actually Cr2 or 7,2-. Potassium dichromate 6. This is another very common oxidizing agent together with KMNO form. If you write potassium dichromate without the 6, you will have made a mistake. If you don't know the formula of the dichromate, you will have made a mistake. This is about valency. Valency is based on the charges of the ions, and you know about lowest common multiple from primary school. We are canceling out the charges by having 2 of the +1 and 1 of the -2. This is what we label how many. That was the idea behind how to construct the formula of an ionic compound. You get 2 K+, and you have 1 of the Cr2 or 7. Each of that chromium is +6 oxidation number. You can't see it because it's combined as a compound. So as a compound, K2Cr2O7 does not have an overall charge. Compound doesn't have charge. Oxidation number of the compound is 0. Potassium in a compound as a group 1 metal, there are 2 potassium, each of which is +1. There are 2 chromium, so there are 7 oxygen, each of which is -2. Oxidation number is for 1 atom, the charge that 1 atom or each atom will have if you form an ion. So we don't want 2 chromium, we want 1 chromium. So 2 chromium is +14 -2. Arithmetic, keep this one here. Move the -14 to the other side, become +14. Move the +2 to the other side, become -2. Arithmetic is primary school mathematics. And this one gives you +6, just like that. Similarly, you also have this thing called Chromat 6. This one will become very important towards the end of your year 10 chemistry. This is with 1 chromium, but for oxygen, it's also +6 oxidation number, CrO42-. The charge of an ion is the oxidation number of the ions, so that you have 4 times -2. For the 4 oxygen, you have 1 chromium. The charge of the ion is the oxidation number of the ion. Chromium is +8 -2, chromium is +6. The same oxidation number, but the different formula of the ions, and they have different names, and these were year 9 names, just like you will know. This is manganese 2+, this is manganese 7, this is your purple color solution. Read carefully, that is VII, and that only then is MnO4-, because there is something else which is called manganese 6. This is MnO4 2-, this is 2-, this is -1. This is your purple color solution. This is not purple color in solution. -2 equal to manganese, +4 times -2. Manganese equal to +8 -2. One small change in the number result in a different name. This is manganese 6 because it's manganese combined with oxygen, but it has Vi because it's a +6 oxidation number, and so on and so forth. In terms of oxidation number, I've just shown you a couple there. You should be able to define redox reactions as simultaneous reduction and oxidation. That means happen at the same time. So question will not ask you what is redox. Question will really, most likely, as you have seen when you did corrections, when you did the actual questions, you did not just do it for fun. You did not just do it because you were living and breathing oxygen. You did it because it was part of the learning process, and you did corrections because you wanted to improve. Unless you just think that, you know, doing things is just the way it is, then it's just the way it is, okay? It is what it is. You are who you are because of what you choose to be or who you choose to be, okay? Now this happens at the same time. So that means explain why this reaction is redox. Why this is redox. If a question say why this reaction is redox, it's not just writing down the definition. You have to show the reduction, and then you have to show the oxidation, because based on the definition, there is reduction and there is oxidation. So you have to show both of them in order to get the mark why this is redox. There are 3 definitions here, but I'm pretty sure in my notes I talk about 4, which include the other one, which is loss of hydrogen. You don't really do it in the new syllabus anymore, but it will become more important as you go to year 11, organic chemistry. Now, this gain of oxygen and loss of oxygen links very well to gaining and losing hydrogen. These 2 definitions go together, especially in the context of organic chemistry, because when we talk about organic, we don't really talk about metals. We talk about the carbon, the hydrogen, the oxygen, and therefore, the gain and loss of these oxygen and hydrogen is more important in the redox chemistry of organic compound. Whereas when we talk about metals, we are more likely talking about electrons as well as oxidation number, and that is inorganic chemistry. And there's a big branch of inorganic chemistry coming out in the last term of your year 10. A lot of it comes down to periodic table, understanding periodic table. We know that loss of electrons correspond to an increase in oxidation number. Well, I know that, you might not know it, but let me just show you how to write half equation. Half equations are called half equations for a reason. Must have electrons. You must have electrons on the left or on the right. So that means you have either oxidation or reduction. We know about the acronym or RIC. Oxidation is loss of electrons. People are very good with knowing definitions, but what people are less good about is knowing that you have to write a balance equation. Sodium lose electron, become Na+. You lose electrons, you have more protons than electrons now because your identity hasn't changed. Same number of proton, you lose electron. Therefore, you add 1 electron there because you lose 1 electron, you have a +1. Overall, 0 charge on the left, +1 times 1, -1 times 1, +1 and -1, 0 charge. Atoms are balanced, 1 sodium and 1 sodium. Balanced atom, balanced charge. That was all part of the examples in your Redox notes, which you need to go through if you are not very comfortable with these. This is plus electrons on the right-hand side. So this is loss of electron. Sure, why this is oxidation? Because the sodium atom loses electron. Not the Na+, the sodium atom loses electron. Loss of electron is reduction. You can also say in terms of oxidation number, if the question doesn't specify. Sodium as an element is sodium 0. Sodium as an ion, the charge of the ion is the oxidation number of the ion. Increase in oxidation number is also oxidation there. Question might say, explain in terms of electrons why this is oxidation. You must talk about electron. Explain in terms of oxidation number why this is oxidation. You must show the oxidation number from what in what to sodium +1 in Na+, and therefore this is oxidation as the oxidation number increases. But if the question never specify, explain why this is redox. You can use either the loss of electrons or the oxidation number. There are no oxygen or hydrogen here. If you use that definition, you know you're not making any sense at all. Before you choose, think before you choose which definition you have to use, and you have to know all definitions, of course. Now, in terms of the non-metal, such as the halogens, which exist as a diatomic molecule, as an element, as you know, chemical bonding, covalent bonding, fill up the valence shell. And then this one will gain electrons in order to give you the anion, which have a fully filled outer shell, and you can draw the dot and cross for that. So what happened there is I have 2 chlorine atoms. So I need 2 chlorine atoms there, but I also have a -1 for each chloride ion. -1 times 2 is -2. No charge with the molecule, 2 electrons there. This is plus electrons on the left. This is gaining electrons. Reduction is gain of electrons. Chlorine as a molecule, as an element, is chlorine 0. Chlorine -1. Oxidation number decreases. This is reduction there. What is more important is how do you combine half equation together? This was also stated in the notes last year. When you have oxidation, you can combine with reduction to get to a complete balance equation, because that is lowest common multiple. That is just balancing equation to get a redox. Redox equation is the full story. You want to have 1 electrons there, 2 electrons there. So what you do is you will multiply this whole thing by 2. When you multiply by 2, it's everything on the left and on the right multiplied by 2, so that you get 2, 2, and 2, like that. So you don't just put the 2 in front of the electron, but also make sure you do whatever on the left and on the right. Then you add up the oxidation and reduction. On the left, you get 2 Na, and then you have 2 electrons and Cl2, and you get 2 Na plus 2 Cl minus plus 2 electrons. Whatever on the left is on the left, whatever on the right is on the right. The 2 electrons and 2 electrons cancel. That was the very reason why you did lowest common multiple in the first place, and you will see that the 2 Na plus the Cl2 give you 2 NaCl. This is an ionic compound. It has a giant ionic structure. This is a covalent element is a simple covalent element because it has a simple covalent structure. Sodium is an element, it's a metallic element. It's a metal, it consists only one type of atoms, it's element. It is compound, it consists of alternating cations and anions because it's actually a giant ionic structure. The structure looks like that. This is alternating cations and anions in a repeated array. This is giant ionic structure. But then originally, your metal does not have anions. Your metal, sodium metal, has a giant metallic structure, as I did mention in the previous review. Is actually the cations, and these cations are surrounded by your electrons, which are negatively charged. And these are the delocalized electrons. That's why you have free electrons. There are no free electrons here because the electrons are all transferred from the metal to the non-metal. There are no free electrons lying around. They are all in the shell. These are cations and anions. Solid state, there's no free ions. Solid state metal, the cations are packed tightly, but they've got interspersed in between delocalized valence electrons, and these are the ones that can conduct electricity even in the metal state. And now you have change in bonding, metallic bonds, covalent bonds need to break. Then when you get the covalent bond broken, they get chlorine atom, and they can gain electrons in order to form chloride ion there. So obviously a lot of bonding concept there, but there's a recap of your year 9, and that is why you had a strong foundation so that you can understand what's going on. Of course, people who had taken the shortcut in bonding, yeah, you know what will happen if you continue forward without covering your basic. Now, next one, they say identify redox reactions, could be that, or in terms of oxidation number, they don't mention it, but you could obviously use in terms of oxidation number as well. That's also correct, but question will sometimes give you half equations. So when they give you half equations, make sure you use the electrons. But when they don't give you half equations, and when you can see some of the typical example, the gaining and losing oxygen is not always easy, especially when you have these equations, the hydroxide in electrolysis becoming O2, NH2O, and then you lose electrons. This happens at the anode, oxidation at the anode, because reduction happens at the cathode. You get 2 of that, 4 of that, and 4 electrons. Even though you get oxygen here, this gain and loss of oxygen is not the molecule, it's actually atom. It's one of the trickiest one to do because people are so fixated on gaining and losing oxygen that fail to see the big picture. Your reactant is OH minus. So your OH minus loses electron, not your oxygen lose electron because your oxygen is O2. Your OH minus on the left side loses electrons because your electrons are now on the right-hand side. So loss of electrons is oxidation. You can also talk about oxidation number, oxygen -2 in OH minus, because we just look at one species. This is oxygen 0 in O2 as an element. You don't talk about the water because the water is still hydrogen +1 and oxygen -2. No changes from here to here, but there is a change from there to there. Increase in oxidation number is oxidation there. Now I've just identified all of these previously, but these are just some general rules. They will not ask you like, what are the oxidation number rules? They will not do like that. They will ask you what is the oxidation number of these in this particular species. It all comes down to the general rules, which I have just shown and demonstrated to you with the various examples throughout. The next thing I want to focus on is this idea of oxidizing and reducing agent. Make sure you can define and define. As with any definitions, you have to be able to list down every single definitions you have from year 9 all the way to year 11. Without definitions, you will make mistakes. Definition is the very basis of what is actually happening. If you get definition wrong, you get concept wrong, you cannot apply yourself without a strong definition as your foundation. Oxidizing agent, oxidizers are the substance, and look at the definition. And so that means you have to include a second point. Itself get reduced. Itself get reduced would mean itself could lose oxygen, but not only that, that is probably one of the most useless definition together with this gain hydrogen. So we more easily focus in inorganic chemistry in terms of RIC, which is gain electrons. So you gain electron, itself get reduced. its oxidation number decreases if its surf get reduced. Oxidizing agent will react with reducing agent. Then you get redox reactions. So in a full redox reaction, identify what undergo oxidation, what undergo reduction, and therefore which one is oxidizing and which one is reducing agent. The most popular one is color changes. Color changes. This is acidified. No acid, no redox. You know it. You know it from the half equation. No acid, no redox. Potassium manganese 7, KMnO4, purple color to begin with. Aqueous potassium iodide. All potassium salts are soluble. All potassium salts are soluble. Ki is a soluble salt. It's aqueous solution. It's colorless. Iodide is colorless to begin with because it's a solution. It's not a solid. All potassium salts are soluble. So what I'm going to show you is these reactions. So KMnO4, as you know, it needs to be acidified. So what we write, as I've shown you in the notes from year 9, this represents acid. Acid contain H+. The H+ make the pH lesser than 7. If you don't have acid, the redox will not work. This is the half equation. As with any half equations, even year 9 chemistry students should be able to balance equation now. It goes to Mn2+ plus H2O. There are 4 oxygen. So 4 oxygen giving you 8 hydrogen. 8 hydrogen, balancing charges, no charge, +2. Overall is +2 charge on the right. You need overall +2 on this side. Don't look at the electron first. -1 plus 8 is -7. -7 plus, oh, sorry, +8 is +8. -1 is +7. +7 to become +2. I need to -5, so I have 5 electrons there. As you will know, Fe2+ get oxidized to iron 3+ in the presence of these purple colored solution. Describe color changes. Purple solution to these colorless, but sometimes in titration, you do until you get a permanent pale pink, because when it's colorless, you don't see anything at all. As you know from titration, you read above the meniscus for this particular titration itself. Okay, and then for this equation, you can just multiply this by 5. Lowest common multiple between 5 electrons and 1 electron. You need 1 mole. You need 1 mole of MnO4-, but you need 5 mole of iron 2+. 1 mole of that will react with 5 mole of these because you need to balance the half equations. This could be one of the easiest thing to do in a multiple choice setting. Think about your ratio. These are mole ratio in terms of the electrons being canceled out. 5 electrons on the left, 5 electrons on the right, but not just the electrons, everything get multiplied. Multiply the whole equation to get the full redox equation. Purple to colorless, color change there. You also have the reducing agent, which is potassium iodide. Doesn't need to be acidified. This is a good reducing agent. Now, this can oxidize something else. So, sorry, this can reduce something else. If I react this with iron 3+, I will get iron 2+ plus I2. So I'm just gonna do K plus I minus like that. So this is just the ionic equation. Of course, I can balance it like that, and I actually need 2 and 2 of that. And how do I know that? Because you can start from half equations. This was what we had done in year 9 redox as well. 2 electrons, 1 electrons, multiplied by 2 throughout. 2 of that, 2 of that, 2 of that, 1 of that. Color changes. If this thing is a reducing agent, itself reduces. Itself get oxidized, but it reduces the iron 3, iron +3 to iron +2. So we look at the charge of the ion. So this is reduction. And then the iodine 0 in the element, iodine -1 in the iodide. This is increase in oxidation number. -1 to 0, you have increased by 1. There's oxidation. What happened to reducing agent? It reduces the other species and itself get oxidized. Now, what happened to the other substance? Well, the other substance must be oxidizing agent, because oxidizing agent reacts with reducing agent. That's when you get a redox reaction. Oxidizing agent oxidizes the other substance and itself get reduced. So identify oxidation and reduction, identify in that equation also which one is reducing agent and which one is oxidizing agent, and identify color changes. This one is colorless, but this one is brown solution. Do not confuse yourself with starch indicator. This is brown solution. This is iodine dissolved in water is a brown solution. When you add starch, I2 plus starch, if and only if you have starch, then it will be blue-black, because that is your test for iodine in your, sorry, that's your test for starch in your biology. In chemistry, we are producing the iodine. Only when we add starch, we get the blue-black solution. Otherwise, it remains brown solution. So do not write blue-black unless you have starch. Otherwise, it's colorless to brown solution. Of course, these are transition metal, meaning to say they contain colored solution. Their solution is colored. In hindsight, I probably shouldn't have chosen this example, but the colorless to brown is quite dominating. The brown solution is quite dark compared to this color in solution. I just want to highlight something very quickly. This is aqueous, and this is aqueous. There is no hydroxide. You did not add sodium hydroxide. A lot of people are confused between the test for cation and whatever you see here. There is no sodium hydroxide added. So why in the world would you get, you know, a green precipitate or red-brown precipitate? Because that was the test for cations. And in the test for cations, you add sodium hydroxide or you add ammonia. When there is no sodium hydroxide, there is no precipitation, because there is no iron 2 hydroxide or there's no iron 3 hydroxide. These are aqueous solutions. So iron 2 plus is a bit yellowy in solution, whereas iron 3 plus is a bit orange brown in solution. It's a solution. It's not a precipitate unless you added in sodium hydroxide test for cation. That is, in fact, the very next thing I'm going to go through with you, because that is the last thing that we did in year 9. Basically, experimental techniques, you need to know general solubility for salts. So we know that all sodium, potassium, and ammonium salts, these are salts, meaning they contain Na+, K+, and NH4+ is ammonium. It's not ammonia. Nitrate is NO3-, so everything that contains nitrate is soluble. We know also chloride, bromide, and iodide. So chloride is soluble except for silver chloride. And then lead here refer to lead 2 chloride. So lead 2 chloride is also insoluble. So the lead 2 chloride, the lead 2 bromide, lead 2 iodide is insoluble. The color of which AgCl, AgBr, and AgI, these are precipitate. So this is white precipitate, cream precipitate, yellow precipitate, only when you added in the silver nitrate and dilute nitric acid. This is the test for, where's the anion? This is a test for the anion, chloride, bromide, iodide. These are already in solution. You need to add some dilute nitric acid. So there's aqueous dilute nitric acid. Then add the silver nitrate as a solution. This aqueous, as I mentioned and corrected last year, very, very important, because I don't know why that is not appearing. Anyway, it doesn't matter. So what happened then is this one will get a white precipitate. Why did I write in full? Because this is a theory paper, so you are not allowed the abbreviation PPT. This is cream PPT. This is yellow PPT. And the precipitation equation is a very, very popular one. Silver nitrate, all nitrates are soluble. The NO3- is a spectator ion. The chloride that you are adding is also in solution. So it's colorless and colorless solution, and you get a white precipitate. So you get a precipitate forming. This is called precipitation, not a redox, because this is silver +1. Follow the charge of the ions. This is ionic compound, silver chloride, giant ionic structure, no changes in oxidation number, not a redox there, but it is a chemical reaction because they are just coming together to give you this precipitate now. Whereas previously they were part of silver nitrate and maybe sodium chloride or potassium chloride or whatnot. And anyway, I'm doing a syllabus review, so I'm not going to go through everything here with you. And you know about sulfate. So barium sulfate is a very common insoluble precipitate. That is another one, test for sulfate by using barium nitrate or barium chloride. After you add in a bit of nitric acid, there's a test for sulfate there. So what you're going to get is you're going to get barium sulfate, a white precipitate forming. Carbonates, so the group 2 carbonates are insoluble. In fact, all carbonates are insoluble except for these 3, which correlates with the first thing. If you know the first thing there, then you know only these 3 carbonates are soluble. In fact, the next one, hydroxide. This is the very reason test for cation. Why in the world do we use sodium hydroxide or ammonia to test for cations? Because the metal hydroxides are insoluble except for sodium, potassium, and ammonium, because all these 3 of the hydroxide, they are soluble. Ammonium hydroxide is actually ammonia. When you think about it, ammonium and hydroxide, what do you get? You get ammonia and water. When ammonia dissolves in water, they give you ammonium hydroxide, but it is in equilibrium, and we'll talk about this more in acid and bases topic. Calcium hydroxide is a strange one. You know about lime water. So calcium hydroxide saturated is lime water, and it goes back to your 2 pages qualitative analysis, and you know about this thing here. So calcium hydroxide, it does give you a white precipitate in a large excess of that hydroxide. You're gonna form this calcium hydroxide, which was partially soluble. Unless you have a large amount of hydroxide, then it crashes out as a white precipitate. Now, saturated means as much of it as possible in a given volume at a particular temperature. Saturated solution of calcium hydroxide is what you call lime water. Lime water is used to test for carbon dioxide. So carbon dioxide plus calcium hydroxide. This is acidic, this is basic. It's going to give you a salt, and it's going to give you water. All the group 2 carbonates, in fact, all the carbonates, calcium 2 plus, CO3 2 minus, all the carbonates are insoluble. This is a white, a chalky, a cloudy precipitate. It confirms CO2 gas is present with the lime water being added. So all the group 2 carbonates are insoluble. All the carbonates are insoluble except for these 3, because all potassium, sodium, and ammonium salts are soluble there. All right, so jumping straight onto experimental techniques. I only have like 5-10 minutes. So I won't really be going through everything, of course. So we skipped all those topics and we went straight to experimental chemistry. I did ask you about all of these apparatus. So all of you should know how to spell properly, especially for burette, okay, and as well as pipette. So some of the people always misspell these 2. The balances there refer to mass balance. Typical mass balance in the school laboratory can be 1 decimal place, can be 2 decimal place. We don't use the one which rounds up to whole number. Those are typically what you use in the kitchen. So we use this term called stopwatch, but question can sometimes use something called stop clock. So stop clock is the same as stopwatch. It's just that we use stopwatch even in physics, even in biology as well. The thermometer that we have in the school laboratory, when you do an actual experiment, it's accurate to the nearest 0.5 degrees Celsius. So that means whatever reading 0.0 or whatever reading 0.5 is essential, which includes the difference in temperature. In physics, you call this delta T, which is your final temperature minus your initial temperature. Could be positive when you have an increase in temperature, could be negative if you have a decrease in temperature. You know, increase in temperature of the solution get hotter because the reaction is exothermic. That's why your solution increase in temperature. But when this is negative, your solution gets colder because your solution loses energy to the system. Your reactant takes away the energy from your solution. It's an endothermic reaction there. Now, measuring cylinders comes in various sizes, but measuring cylinder is definitely less accurate. What does it measure? It measures volume of solutions. So less accurate than burette or pipette. So burette and pipette is going to be more accurate than measuring cylinder, but measuring cylinder is more accurate than a beaker, for example. So how do you improve accuracy? You can not use a beaker. You can choose to replace a measuring cylinder with a burette, for instance. All right. But advantage would be measuring cylinder, you can have up to 100 cm cube, up to 250 cm cube, up to 500 cm cube, measuring cylinder is okay. But the limit with burette is 50.0 cm cube. You do burette reading to 1 decimal place for your O-level, IGCSE level chemistry. So this 14 to 16 years old chemistry, you have to give the burette reading to 1 decimal place, including the initial, the final, as well as any difference in the burette reading has to be 1 decimal place there. Gas syringe is to use to collect the volume of gas. Measuring cylinder can collect volume of gas, but between gas syringe and measuring cylinder, gas syringe is more accurate than measuring cylinder. Gas collections can happen over multiple ways. 2 of the most common way will be displacement over water. So this one you have seen in the lab, and you will get to do this experiment again and again when we cover rate of reaction. So we displace over water and we will produce bubble, and these are measuring cylinder, and this is collection over water, and the gas will displace the water. Now what happened is this might not be suitable if the gas is soluble in water, such as carbon dioxide. This method is not the best in the world because your carbon dioxide collected will be lesser volume and therefore result in lesser mole of the carbon dioxide, since the volume that you collect will not be accurate because carbon dioxide can dissolve in water. But hydrogen and oxygen should be okay. Oxygen, a little bit of it does dissolve in water. You see people selling oxygenated water. It's just a gimmick. It's just dissolving oxygen in water, not very soluble. You're just pumping in more oxygen in the water. Okay, of course, you can then use a gas syringe. So make sure you have an airtight system. Why do we need an airtight syringe or airtight system? So the gas flows in there. So gas syringe more accurate than a measuring cylinder. So it's got a piston, and this piston has got rubberized end so that the gas will escape on the side. So they're tightly held by this rubberized piston here. And then as the gas forms, they collide with the walls. They collide with the walls with force. Force over area is pressure. Gases exert pressure. And you know about this from physics, and you know about this in kinetic particle theory, the relationship between pressure, volume, and also temperature. Suggest advantages and disadvantages of each method and apparatus. These are all suggestive questions. There is more than just whatever I could set out, but typically the difference will come down to accuracy. So is your equipment better or worse? So the more expensive your equipment is, the better is the accuracy usually. And then this is also about method. So you could be thinking about reliability. Reliability means consistency. So in titration, you will repeat in order to get a reliable or consistent titer. When you do experiment like masses or temperature, you can repeat the experiment. When you repeat the experiment, then you can get reliable results, because you are making sure that when you repeat the experiment, the result should be similar for the previous result you have obtained for the same condition. Okay. In terms of accuracy, it's accuracy, it's not really reliability. Now, the very last thing I want to highlight to you, which I did before, is something called fair test. You learn about fair test probably in biology or primary school math. You change one thing at a time, change one variable at one time. This becomes more important in the next topic on rate of reaction. You could have many factors that could affect what you're trying to investigate. Okay, so if I'm trying to investigate who is the tallest in the class, Later I have some human being, and then I put in some animals. Then it's not really a fair test because I'm changing the species, human, animal, whereas I'm trying to investigate the height. Okay, so I should only keep to human for all my experiment so that I'm not changing the species at all. So that is a fair test. Okay, what I don't change is what I call control variable. Control variable means not changing. It is something that can affect your experiment, but you don't want to change it, not changing. This is versus independent variable. Independent variable is what you change. What you change is called independent variable. So typically what we change will be the x-axis, usually, okay? Usually what you change is the x-axis, is the independent variable. Now, dependent variable is what you measure or what you record. So what to measure or what to record, this is typically the y-axis. They might be processed before they go on the y-axis. Why are you so dependent? Why are you so dependent? That is usually how I remember. The y-axis is dependent variable. The y-axis is what I record. Okay. Now the next thing is describing solvent solute solution, saturated solution. Quite a few of you don't know the definition of saturated solution from last year, but this is in the syllabus. Whatever is in the syllabus, the smallest thing that you think, man, they're not gonna ask it when it comes up, they can simply say it's in the syllabus. You cannot blame them because they told you for the 2023, 2024, 2025, they can ask you anything. Candidates should be able to. So each of these could be a definition. It could be a label, okay? Now labeling residue and filtrate, which one remains on the filter paper, which one remains in the distillation flask, which one remains after you evaporate all the solution. Filtrate is the stuff that passed through the filter. I think that one is okay. Describing acid-base titration. If you have done acid-base titration, you should be able to describe it to someone. You have done, I think at least, each of you must have done at least 2 or 3 acid-base titration, as well as some including redox titration. You need indicator. You also need to know their color changes. I try my best to actually make you have that experience. And we try to go through it with examples from alternative to practical, as well as your topical test questions. But the rest of it is really down to you, whether you could recall the experience, whether you actually use your experience to the fullest advantage or not. Like I said again and again, your memories will fade unless you use it. Burette and pipette. What do you normally do with pipette and burette and that kind of stuff? And what is endpoint? Be very careful with like a redox titration, especially when your purple colored KMNO4 is in your burette and you keep on getting colorless in the conical flask. You do not stop when it's colorless because you don't reach the endpoint yet. So it will be purple to like permanent pale pink because one extra drop, that was your experience. One extra drop, then there was the endpoint there. As for chromatography, make sure you could spell it. There were specific procedures that you need to get to chromatography. There are 2 or 3 steps. So that is why it's called describe. Describe how to separate. So you need to prepare. You need to prepare. Okay, there are some fixed essays. You can look at your work, the alternative to practical work. Very common in alternative to practical. Make sure you know how to extract like the colored pigment. You need to use a mortar and pestle, and then get like the colors, and then put the dots on the filter paper, and then draw the solvent front. Solvent front is where the solvent stop. Draw the what's that thing called? Baseline. Baseline is where you start. And make sure you know about cover with a lid because your solvent can evaporate, especially if you use a volatile solvent. When there is no more solvent, there is no more chromatography or separation. Talk about locating agents, like when you have amino acids, colorless substances, or some other stuff which are colorless. Things like metal ions can be colorless unless they are transition metal. Okay, unless they contain transition metal, they will be colorless. Things like amino acids, they will be colorless as well. And then of course we use RF. So state and use the equation. Use the equation is calculation. Stating there is definition. Question will ask you what is meant by RF. No need to write in words. Make sure you're able to write the equation itself in terms of using this point here. So travel by the solvent from baseline. Typically, I remember it like that. Travel by the solute. This is the substance. This is the solute. It's not to the solvent front because only the solvent goes to the solvent front. The solid will not go to solvent front unless it has RF value of 1. Now, nearly the end here. I'm just going to cover until here. So we talk about filtration, separating insoluble solid from soluble solution. Sorry, from a solution. Crystallization. When something is soluble, you cannot filter them. You have to do crystallization. You heat until saturated. You do not heat until dryness. You heat until solution is saturated. And then the second point is you allow the saturated solution to cool. That was what you did when you formed the CuSO4, the really nice blue crystals, which you got to do quite recently, a few months ago. Allow the saturated solution to cool, and then crystals will form. And when the crystals form, they become solid. You need to filter. You filter the crystals and you collect it as residue. Then you wash. You wash with cold distilled water. We never use tap water because tap water contains dissolved ions and they introduce impurities. The difference between simple distillation and fractional distillation, not that big of a difference, but fractional distillation, when you have multiple fractions to separate out, like A, which is your 78% nitrogen, your 21% oxygen, you also have 1% CO2 and argon and etc. etc. So around 0.03% CO2 there. So argon, oxygen, and nitrogen, they are obtained by fractional distillation of liquid A and not obtained by simple distillation. Simple distillation, typically just to separate out water from salt, typically just to separate out ethanol from water. So just to separate out two things. Fractional distillation is also in crude oil. So your crude oil could be separated into many fractions. You will learn more about this in year 11 organic chemistry. Okay, and what else? Pure substance will have a fixed melting point and boiling point. And when you have a mixture, they will melt and boil over a range of temperature. That is something that you have learned from structure and bonding, as well as kinetic particle theory. I won't go through all of these, but I just want to highlight that sulfite is in the theory. It's not in the 2 pages test from paper 3, but it is in the theory. Describe the test, identify the anions, including all of these. The steps are required, and you don't memorize this by reading. You have to close your eye and imagine yourself doing it, because you have done each and every one of these last year. Prior to the school closure in August, I think I made sure that you had this experience, and experience cannot be bought, and experience can only be relived. You have done it. You have to dig back on those memory and think about what you have recorded for your own observation last year, your own observations, your own handwriting, your own memory. Okay, and all of these are tests for gases. So make sure you know the difference between tests for ammonia versus ammonium. And some people will confuse tests for sulfate versus SO3. These are ions, these are gases. Some of these tests for ions, they release gases as well. So make sure you are aware of all those things. Describe the test doesn't mean just in a little bit, in a small amount of the hydroxide. And what happened in excess, that is very important. Okay, so follow the questions and you should be fine. A lot of people, they forgot some important case studies. The chromium 3+ versus the iron 2+, these are very commonly asked. Aluminium 3+ versus zinc 2+, very commonly asked. What else do they like to ask? Ammonium ion. Ammonium ion is very commonly asked. What is the other one? Iron 2 versus iron 3. That one is quite commonly asked as well. And last but not least, the chemistry of copper 2+ is very commonly asked. As you can imagine, chemistry of copper 2+ can be combined easily into electrolysis topic. As you have done quite a lot of those, they can mix and match some qualitative analysis question in there as well. They can also mix in some crystallization questions, how to produce the crystals, the copper 2 sulfate, the blue crystals, which you formed last time in terms of the steps. They could also ask you to do some mole calculation, the hydrated, where was the hydrated? The hydrated salt, you know, the water of crystallization, something dot something H2O. So CuSO4 dot 5 H2O, what is meant by that? How do you find the value here if it is X in terms of mole calculations? All of that was something you had done in year 9, either as your topical test, or either as part of the exercises, or as part of the practical experiment which you had done. Okay, I've gone beyond my time, so I better stop there. That's it really for year 9 review. So I hope that was useful. The video will not be uploaded today, unfortunately, because of some technical issues. So yeah, it will be uploaded tomorrow. So I'm in the school lab at the moment, but you guys are at home. So I hope that was quite intensive, obviously, but that was all just a review. No matter how many times you listen to me, or watch all my videos and whatever, if you haven't done anything on your end, it will not change. Your situation will not improve unless you work for what you want. Okay, you go from your poor state to an improved state only by getting your hands dirty and actually writing. You don't get better just by reading. You don't get better just by watching. You get better by writing and connecting dots together. The way the brain memories work is you need to jot back the memory, okay? And you need to link the different topics together. I try my best to link the topics for you, but you have to be able to link it together and tell yourself the story in a coherent manner. If you can tell the story on a piece of paper to yourself, you will be fine. You can tell the story to your friend, and your friend can, check with you. Your friend can go through the story, their story with you as well, and that will help each other as well. But be careful with the friend you are, cross-checking with. They might teach you the wrong stuff, or they might let you get away with the wrong stuff. Okay, so that's it really for today. Let me just take a quick attendance, and I think almost everyone is present. I think, except for I know a couple who are not here, but that's all right. Yep, I could ask you to turn your camera, but I really don't want to. Let's just call it a day here. I'll see you guys next week in school, yeah? Next week is topical test for chemical energetics. All right, take care, everyone. Thank you.